Hello, today we will be doing a single target plot with a course and or speed change. If you're following along with the Rapid Radar plotting packet, we are doing plot number 4 on page 31. Now, to start off, we have our own ship info with a course of 000 degrees true and a speed of 10 knots. So go ahead and write that on the bottom right corner of your plotting sheet. Now the time is 12 o'clock. We take our first range and bearing of our single target. It is bearing 68.1 degrees true at a range of 4.4 nautical miles. Now, since we're only starting at a range of 4.4, we can assume we can use the 6 nautical mile distance scale. So let's plot that first range and bearing. Again, I like to always do my bearing first and then go in with my range. Make sure you have lead, sharp lead, on the end of your dividers. Precision is key with radar plotting. Once we plot that point down, we label it R with the time 1200. And I just like to clean up my point right there just for clutter later on. So again, R 1200. Now we take a second range and bearing at 1205. But as we're waiting for that 1205 to even happen, that's 5 minutes of waiting, we could start figuring out where our E exists. So if our course is 000, we are doing the reciprocal of 000. So drawing a line 180 degrees from R. Now, already getting ready to plot E will help you when you are plotting in the radar simulator lab and you have to go very, very fast. I mean, between our 12 o'clock first range and bearing and our 1205 second range and bearing, we have a little bit of time to spare. So all I did was create the reciprocal for E. We'll come back to that. Maybe I don't know my full time signature yet. So now I'm plotting my second range and bearing at 1205. I have a target, that same target bearing 67.7 degrees true at a range of 3.8 nautical miles. So again, I make my bearing first. I go in with my fine-tuned dividers with the wheel. Again, sharp lead, very important. And this point will be labeled M, 1205. Now, I already wrote the 1210 information in the boxes. So at 1210, we have another range and bearing. This target is at 1210 bearing 67.0 degrees true at a distance of 3.3 nautical miles. So I plot that, and this will be labeled my M2 with a time signature of 1210. Okay, now I can finish creating where my E was supposed to be. I know now my biggest ERM triangle I can make is my 1210E. So now I'm doing my 60D Street math to find where my E should be. Again, I have a 10-minute interval, and my own vessel speed is going 10 knots. So with 60D Street, I plug in my speed of 10 knots and my time of 10 knots. 10 times 10 divided by 60, I get a distance where my E should be of 1.6 repeating. Again, we are doing this measured distance from R. So 1.67 away from R, make a little point, and that is my E. Be sure to always timestamp what your E is. So E 1210. Okay, fantastic. Now I'm going to go continue plotting the rest of my relationship. So I'm going to connect my R to M's to create my relative motion line, and I'll be able to see how close they're going to get to me. Now I'm going to connect my E to my M, and I could see this vessel's E to M true motion, which way they're facing, to help me with rules of the road situations. Now, for just this video, I am not going to solve for everything, not their true course and speed, not their relative motion course and speed necessarily. I'm just going to go as if I'm plotting in the radar lab and I have to solve immediately for my new course or speed change. Because obviously we could see in this plot visually that they are going to get pretty close to my bow. So we are given a minimum CPA to maintain as 1 nautical mile with a MX maneuvering time of 12:20. I usually like to write that on the bottom. So we can clearly see their relative motion line is going right through our 1 nautical mile CPA. But where does their MX time even exist? Well, first, we want to find their relative motion speed. Now, we could find MX one of two ways. We could use that relative motion speed to figure out where they'll be in the future, or if it is divisible by the time increment we're choosing, we could simply just move our dividers over. I'm going to do the math version first. So my distance between R to M was 1.12. I multiply that distance by 60, and then I divide it by the amount of time, which was 10 minutes. So I have a relative motion speed of 6.72 knots. Now with that relative motion speed, I can now find where my MX should be located. So my MX is at 12:20. That is a 20-minute difference from R. So that's my time. My speed is my relative motion speed I just found. Divide those by 60, and I will get the distance of where my MX should be on the relative motion line from R. And just make that mark lightly. I label it MX with the timestamp. Now, the second way that we could have found that MX is 12:20 is divisible by our 12:10 triangle. So if we measure our R to M2, our 12 o'clock to 12:10, it should be the same distance as our 12:10 to our 12:20. So that's a quick way to figure out where your MX should be located. Okay, now from that MX, that is where I will be actually turning. At 12:20, my vessel will turn. It will turn in such a way that this boat relative motion line goes outside or tangent to my 1 nautical mile CPA. So that is my new relative motion line. Now we know it's going in that direction, above us, because we're going to take that vessel's stern. We are the give way. So I have that new relative motion line. First step to figuring out our new course and speed is I'm going to move MX to M. Now you see how I'm kind of in that circle inside my CPA? That's totally fine. All I have to focus on is actually lining up the line on my triangle to where it should be. If you misdraw it, that's okay. So I'm moving my MX backwards to M. Again, steady hands, drawing that line in. And now I am going to take my E to R, we are E to R, and swing out my R. And see where it intersects with that backwards relative motion line. That is my R prime. That is representing the relationship between E to R prime as my new course. So we can connect those. And I'm using red so it stands out a little bit more. That red line, that is our new course that we will be turning to at 12:20, the time of MX. Now I'm going to take that little line and move it back to the center to see what that angle actually is. Now for this plot, the correct answer is anywhere from 040 degrees true to 045 degrees true. That is from a computer simulator, not myself, trying to negate any human errors. So what I got from my plot was 045. So I would say I would be changing course. I would be a giveaway vessel, changing course to 045 in case of collision. Okay, now let's try to find our new speed. So our new speed, we have E to R, our original, is our original course. We simply just measure E to the intersection on the way to R. So where I highlighted in green, that represents just our speed change. Because if we're not changing course, we're still going 0, 0, 0. So we measure that distance. It's a 10-minute interval, and we just do 60D Street. Now we could use our brain a little bit on this too. Visually, we were originally going 10 knots. That intersection isn't quite halfway through. It's a little bit, more than halfway. So we know we're probably going more than 5 and less than 10. Mathematically, I got 7.32 knots as a speed change. And, visually, that works out. So that would be my new speed. And that's all we have to do for a new course or new speed change. I hope you enjoyed this video. We didn't go fully in depth with solving for everything, but again, if you're following along in the packet, it has the answers for everything else. I'll put it down in the comments for you to check in for as well. And that's it. Bye.